Good evening everyone. Welcome to today's problem solving section week 4 digital VLSI testing course. So today we will start discuss about the test pattern generation. So first introducing the test pattern generation. The test generation is very important in the VLSI testing, and ATPG is something like is an automatic test pattern generation. The full form for ATPG is automatic test pattern generation. Uh, okay, is it audible now? So we will start with the test pattern generation. Test pattern generation is very important in the VLSI testing. So, and it is like ATPG means the full form is the automatic test pattern generation. And our goal is to generate a test set which is small and effective, and also it's at a low computational cost. So ATPG is very challenging task, and its exponential complexity as the circuit size increases, and also the clock frequency, as the frequency of the clock increases, we need some testing methods for delay testing as well. So for higher clock frequencies, we need delay testing methods. So we also model delay defects. So in the conceptually, ATPG is like we have a defect free circuit from which we obtain the golden response, and we have a defective circuit. Now this output is the faulty output, or the output of the circuit which has error. Now this output is compared to both of this circuit, the same input is applied, and this generates a vector, whether like if it is different, then output is 1, that is fault is detected. If it is same, output is 0, so the fault is not detected. So the fault model uh, we have is like so instead of targeting at a defect level, we are modeling it at a higher level at the fault, and we model that and call as fault model, and to capture the logical effect of the underlying defect. So this is to like, use it to capture the logical effect at of the underlying defect. So we have few fault models which include stuck fault model, bridging fault model, and for the delay testing we have path delay fault model and transition fault model. So if to just start with a simple illustration of an ATPG, if we consider this as the circuit, this OR gate with an AND gate A, B, C, D, E. If this is stuck at 1, the D is stuck at 1. This So we need an output which is distinguishable between the faulty and the fault free. So here to excite this fault, we need an opposite value. So we set it to be 0. So to excite this fault, we need an opposite value. So we need to set it to 0. To obtain a 0 here, or get both the inputs should be 0. And to propagate this fault, yes, any doubts? Okay. So to we have obtained this, so we have excited this fault. Now we want to propagate this fault. To propagate this fault, we want a non-controlling value here. So we need to apply 1 at the C. So the required test pattern is 0, 0, 1. So this approach of like getting the exciting the fault, obtaining the input, and then propagating it to the primary output. So this we will discuss in an algorithmic way using the ATPG algorithm. So if we apply this pattern, we can observe that output for a fault free will remain 0 and for a faulty it will be 1. If it is 0, so it should be 0 fault free and faulty it is 1. So it's like fault free by faulty. So in a typical ATPG system, we will generate a test, say for an undetected fault. We will have one set of fault list. So we will pick one fault, we will generate the test. So that this list will contain all the undetected fault. Now, once we get this test vector, we will drop all the other faults which are detected by this test pattern. So we will have some other faults, say it is F1. This vector, when we do simulation, we see that it also detects F2 and F3. Then from this fault list, if it contains say F1, F2, F3, now we will drop this F1, F2 and F3 and the next test will be to detect F4, and if this pattern is also detecting F5 we will drop both this. So this is how we like, and then we repeat the process. So first like generate a test for an undetectable fault and then we drop all the faults which are detected by this test vector by performing the fault simulation. And next we repeat this step until this list we have considered all these faults. And also sometimes some faults are untestable faults. That means no test pattern can be generated for such faults. So such we have untestable faults. So this faults the test cannot be generated. Or for an ATPG, it's an algorithm. So we just set some, we will set some abort limit, or this much time you can search for generating the test pattern. And the aim of the ATPG is to get higher fault coverage in a shorter time, like with lower computational complexity. So once we see that it is that fault, to detect that fault, the test pattern is exceeding that abort limit, we will remove that fault from the list. Such faults also remains untestable. And another method to generate the test pattern is random pattern generation. Random test pattern generation, the random patterns can detect up to 70 to 75% of the faults. So it's a very simplest form. So we just need to generate generating the random patterns. So if n tests are like randomly generated, the probability that T can detect all structured faults is in a given circuit. So the quality of this random pattern will depend on the circuit. Some circuits may have some faults which are also known as random resistance faults. These faults are faults which cannot be detected by the random patterns. That means, for example, if we have an 8 input AND gate, the probability of generating 1 at the gate output, we need 1 in all the outputs. So its probability like 0.5 because either 1 or 0 to the power 8, which remains very low. So we can have some weight to this, so that with we can say that with the probability of 0.75 we are having an input to be 1. Then with this bias, this probability of generating the 1 at the input increases. So the probability to detect such faults which requires 1 here increases. So this is called weighted random. Uh, this is called as the weighted random test generation. Randomly patterns are generated, but we add a weight, increase the like for the one we add the weightage bias term so that we can generate the pattern for detecting such fault which require 1 here. And the goal is to increase the signal probability for the hard to detect regions, like hard to test region. If we have some region and this region remains hard to test, we add a bias term to this to make this region testable. So the next is the probability of fault detection. So given an circuit with n inputs, the TF with the test vectors, set of test vectors that can detect fault F, then the probability df is Tf power 2 to the power n. So is the probability that F a fault can be detected by a random vector. So now EF is the probability that the random vector cannot detect F is 1 minus F. This is able to detect, so 1 minus EF. Now if we have n such vectors, then n random vectors, so its probability is power n. So thus the probability that at least one out of the n vectors can detect the f is 1 minus 1 minus df power n. So this is the probability that at least one out of n random vector can be can detect f. So this is about the probability of detection. Next is the minimum detection probability. The minimum detection probability of any detectable fault actually does not depend on the this n number of inputs, the number of primary inputs. Instead, it depends on the largest primary output pone that it is in. So if this is the fault, the largest the primary output pone for this is the PO is 4. So this is because any detectable fault must be excited and sensitized to the primary output because this fault has to propagate to the output. So with this we have one theorem. In any combinational circuit with multiple outputs, if n max is the number of primary inputs that can lead to a primary output, the detectable, the d min is given by 0.5 to the power n max. 0.5 because any node can be set to either 0 or 1. So this is the detectable probability for most difficult detectable fault. So the next we will see is the exhaustive. Okay. The other is the exhaustive testing, which we have already discussed. Like, can we apply all, if we have n input combination circuit, can we apply 2 to the power n combination? So, this guarantees reduction of all the faults in the combination circuits, but the test time may be prohibitively long if the number of inputs is going large. So, this exhaustive testing is feasible only for the smaller circuit. And another thing is that pseudo exhaustive testing, can we just test if we have one fault? Can we take the logic cone, respective cone, and then perform the exhaustive testing for each of the cone? So these are with respect to exhaustive and pseudo exhaustive test. So next we will see the Boolean difference based method, which is um, the if we have any circuit, for example, this, and let's consider some one basic circuit. So if we can have what the function of f is, it is xy or y bar is z. So let's have we'll consider one fault. The target fault is y is stuck at 0. So this is stuck at 0. Then the fault, we want the faulty and the fault free values to be different. So to obtain the faulty circuit, we want y to be permanently equal to 0. And say f dash is when f of y is 0. So we want this f, and we have seen that XOR operation between this faulty and fault free should give 1. To obtain this, now we will have a difference equation, which is when we substitute at y the 1 and perform the XOR operation. This is the fault free circuit, like we excite this value by giving 1. So fault free value y is 1. But in the faulty circuit, the y value is 0. So now to this difference equation, if we apply this, notice value, y is stuck at 0. So we want a 1 here. So we want to multiply with this. This will give us the test pattern. So now let's do this. Y. What is the y equal to 1 equation if we substitute here? It is x plus 0 z XORed with what will be the, this will be 0, this will be 0, and this will be 1. So it's z. So it will be y x bar z plus x z bar y. So the test pattern will be 0 if I consider x bar yz plus xy z bar. The xyz test pattern will be 0 1 1 or 1 1 0. So now if you substitute these values, you can verify it from our previous method. We said this to be 1 and we want to propagate this here. So t value should be 0 and 3 is 1. To get this here, we wanted a non-controlling value here and this became 0. So this output is 0 anyway. The C can be anything, don't care. So it is 1 1 0 or 1 1 So this is fine. Z can be, but if we give x is equal to 0, so this is one pattern. The another pattern is this one. So now if we propagate from this part, this is going to be 1 by 0. This will be 0 by 1. If we want to propagate from this, so we want this value to be 0. To get this value to be 0, x should be 0. And we should have a non-controlling value which is 1 here. So it is 0, 1, 1. So we can see either of this test pattern can detect the fault. So this is the Boolean difference based method. If we consider another example using the same Boolean difference based method, now let's detect a fault at the W node. I will redraw this circuit again. Now let's consider the fault in the node W. This node to be stuck at again 0. So the expression we have already obtained, f is xy plus y bar z. Xy plus y bar z. Now the test pattern is we want stuck at 0 here. So this can be excited by applying a 1 here. So y it should be 1. And this value we have to apply, say y equal to 1, write the expression XORed with when y equal to 0. So y equal to 1, it is x. This will be 0. Okay, we want in terms of W now. For W stuck at 1, we want the expression in terms of W. So it is x, y odd with W, where this W is y bar z. Now we have W to be 1, and this is the expression. So let's write the when W is 1 and when W is 0. When it is 1, it is xy plus 1 XORed with xy plus 0. So it is 1 XORed with xy into W. This should be 1. Any number, if we have an XOR gate, if it is writing, I'm just writing the truth table of the XOR. X is equal to 1, y is equal to 1, z is equal to 0. Yes, that is okay. Yes, let's see that. So this expression we have come. Now if we see any value is 1, the output is, if it is different, output is 1. If it is same, output is 0. So you can see if it is 1, output is opposite of it. If it is 1, it's opposite of it. That means it should be W x y complement equal to 1. So what is applying the De Morgan's theorem? So it's W x bar plus W y bar. Now what is the W value? It is y bar z. So we get x bar y bar z plus y bar z. This is, so it can be 0, 0, 1, or it can be 1, 0, 1, or it can be 0, 0, 1. Okay, this is already covered. So these two are the patterns which can deduct this fault. If we try, we want a 1 here. We want a non-controlling value here such that the output fault free is 1, faulty is 0. Now to get a 1 here, we want, it's an AND gate, so we want both the inputs to be 1. So this is 1. This should be 0. So this became 0 anyway. So x can be, I don't care. So it is 0, 0, 1 or 1, 0, 1. So this is the required test patterns. Any doubts for solving using the Boolean difference based method?
Ma'am, how did we take y is equals w is equals to y bar z, ma'am?
Here is, this is the W. So the W value is, here we will get y bar. Here it is z. So W is y bar z. Uh, we wanted W in this
Yes,
F
ma'am.
expression. That's why we just kept it W. It is W XORed with, ORed with X and Y. And while generating, like getting the test patterns, we replaced it with its previous expression, Y bar Z. So now we will go to the next question. Okay, before going to this one, we will solve one more Boolean difference based question. Just get one more new slide. So we will solve one more example. And this time we will keep C stuck at 0. So this is stuck at 0. Now what for this stuck at 0, it should be 1 to excite the fault. So we want to multiply with C. Now what will be the expression of F? It is xy plus xy z. And like, let's multiply. So the expression when z is 0 will be xy XORed with, when it is 1 it's x1 xy plus xy, so again xy. So we can see it is z into 0, which can never be equal to 1. So this fault is actually untestable fault. These untestable faults are also called as redundant faults. Now, if you see this expression, if you simplify using the Boolean algebra, it's like xy into 1 plus z, which is simplified to xy. So, this portion of the circuit is like something redundant circuit. That's why those faults were untestable faults. So, even this ATPG can be used to detect such redundant faults and to simplify the circuit. So this is the portion using the Boolean algebra simplification to show why a fault is untestable, a redundant fault is untestable. So next we will go for 5 valued logic. Yes. Any doubts?
Elements
Yes.
why is X? Why is stepped point? That is, if Z is equals to 0 and X orbit Z is equals to 1. Like here in this equation,
Uh,
Z in that
Sorry,
is
I didn't get your question. Why?
this X, this Z into XY, X or XY, this we have written.
You're asking why this is untestable? Is your question why this fault is untestable?
Yes, ma'am.
Okay. So the fault is untestable because we want this expression. This we got when we applied f is equal to 1, and this we obtain when f is equal to 0. This value, when both are same, 0 0 or 1 1, XOR gives our output 0, and with z. This will always give 0. But we want a faulty circuit XORed with a fault free circuit to give 1 to generate the test pattern. But we are getting 0. So there is no vector possible which can give me 1 to this. So such faults are untestable faults. And this fault is also called as redundant fault, because if you see, you can simplify using the Boolean algebra. This portion of 1 plus z will be removed from the circuit. If you simplify this, it's like just an AND gate with x and y. This is completely redundant portion. Sorry, not this. Yeah, this is. So any fault in this place will be like undeductible faults. Is it clear?
Yes, ma'am. I got it. Yes, yes, thank you.
So the next we will see the five valued algebra for Boolean, like for the combinational circuit. So for some Boolean gates, let's say for basic gates, if we have an AND gate, so first the five valued logic consists of 0, 1, x is the don't kill. So like which can we can say unknown also, which means it can be either 0 or 1. And what is D? D is 1 bar 0, and D bar is 0 bar 1. This is the 5 value logic. So now let's just define this for the basic gates. So this is the normal truth table. 0 and 0 is 0, 0, 0 and 1. Now what will be the, this is, we know it is 1 by 0. It is 0 by 1. 1 or 1 by 0. This means fault free is 1 and faulty is 0. X is like unknown. If we have a controlling value, then we can say it should be 0. Otherwise, it will remain don't care. Again, 0 is a controlling value. Output can be determined as 0. Otherwise, don't care. Next, if it is a controlling value for any one value is 0, the other, whatever is the other input, output is going to remain 0. Now, 1 for 1, it will be giving 1, 0 and 0 will give 0. So it's a D. 0 and 1, 0, 1. So it's again D bar. Again, with this, if we perform 0, 0. So it's 0. 1 and 1, 1, 0, it's D. 1, 0, it's B. 0, 1, it's D bar. 0, 0, it's 0. 0, 1, it's D bar. So this is how we will perform the like 5 valued algebra for an AND gate. Similarly for an OR gate. So 0 is 0, 1, 1, and 1. So this is our truth table. Now when it is a controlling value, so 1 is a controlling value for OR, it will give output to be 1. And otherwise for X, if it is an input with non-controlling, it will be don't care. Now D is 1 by 0, it is 0 by 1, 1 by 0, 0 by 1. Now let's perform for this 1, 1, it's 1. 1, 1, it's 1. Okay, this I made a mistake. 1, this will be 1, 0, which is D. 0, 1, D bar. 1, 0, D. 1, 0, D. 1 or 1, it's like 1, 1, so 1. 0, 1, D bar. 1, 1, it's 1. This will be 0, 1, which is D bar. So similarly for NOT gate, if it is 0, output will be 1. If it is 1, it will be 0. If it is D, complement is D bar and D's bars is D and don't care will remain don't care. So with this logic of like D bar, we will proceed for some algorithmic approaches for the ATPG. And before that, we have something called as branch and bound based method, which is for searching in a using a decision tree. So decision tree means if we have a circuit, for A we can have 0 or 1. For this we have some solution space when A is equal to 1. Similarly, this can go to C. Say C can also have both 0 and 1 input, and this D goes to say 0 and 1. Now this gives to some solution a solution space where A is 0, C is 1, D is 0. And this gives to a solution space where A is 0, C is 1, and D is. And this gives to a solution space where A is 0 and C is 0. So in this way, we just like for searching, we go to say we want to go to A equal to 0. We go to A equal to C equal to 0. We find that there is no solution in this space. We backtrack and then go to the next D. So here we have the concept of backtracking. Say A again. We say that okay, we have A. We explored in C 0, C equal to 0. Sorry, A equal to 0 and C equal to 1. Now we came to D equal to 0 and we found that there is a conflict. So we backtrack and we try the solution with D equal to 1. This is called a backtrack. So as D equal to 1 also causes a conflict, if this is also causing a conflict, instead of this we will backtrack and explore this path. C is equal to 0. So whenever like conflict means whenever we are not able to propagate the D is getting masked. So we backtrack and then go to explore in the another space. So ATPG will search one branch at a time. So this is how the branch and bound based method is working. Now, if we have an ATPG like for circuit for fan out free circuit, what is fan out free circuit is that we don't have, say we have a circuit like this which fan outs to some other. This is called fan out circuit. So a fan out free circuit means it goes to some input. Again, this input is coming from here. So this is a fan out free circuit. So what we perform is that we first initialize all the input values to like all the values to x. That means first we don't know what is the value at all the nodes. The next is that for any fan out free value we are justifying it. So first we want to excite the fault. So we have to apply, if it is stuck at V, we have to apply the opposite value. And next we have to propagate this to the output, any primary output. So what is the procedure algorithm to justify? If we have an AND gate, say we want 1 here, then we want all of these inputs to be 1. So it has to be justified from all the combinational blocks it is connected to. And from this output to the input we call as justification. And similarly say 0, any one node which is like near, we can justify that to 0, which is easily controllable. Similarly to propagate also we have similar algorithm. So you can see if the gate is an AND gate and we want 1, so we want to justify all the values to be 1. If it is 0, any 1 can be justified to 0. And that any 1 can be which is having a don't care value or easily controllable value. And similar procedure for OR gate. Now for justifying the circuit, let's take one example where G node is stuck at 0. So the fault free is 1, faulty is 0. To get a 1 here, we need to first justify this G to be 1. To get a G1, we want a 1 here and 1 here. So we want to justify A and F. To get F as 1, we have to justify a 0 here. So these are the calls made for justifying this 1 here to excite the fault. So next is for propagating the fault. Now to propagate a fault, if we say I have an AND gate, the algorithm says that okay, if this here we have the fault value, the other values should be non-controlling value. And for an AND gate, the non-controlling value is 1, so that it can propagate this fault to the output. So exactly that is described here. If it is an AND gate, we have to justify 1, and if it is an OR gate, we have to justify 0. So similarly with this example, previously we have seen that this fault is stuck at 0. This node is stuck at 0. So now we have to propagate this here. To propagate this fault, we want to propagate this G. To propagate this, a non-controlling value is required. So H has to be justified to 0. To have a 0 here, either B or D has to be 0. So if we can consider this to be 0, the output we will obtain at the C. So this can be done too. So next we will see some algorithmic based methods. Now this was for fan out free branches, but like D algorithm is a algorithm which can handle arbitrary combinational circuits with internal fan out structures. So the main idea is that we have two concepts of D frontier and J frontier. So we want this can be used for any arbitrary combinational circuit. So we want to maintain a non-empty D frontier. We will say what is this D frontier, so that we can propagate this to the output, primary output, and that to at least one primary output. So initially all the circuit nodes are at the don't care value, like unknown value as we have seen already, and at the fault site we will place either D or D bar. So if it is this or this, these are the two possible for a fault effect. So because of this only we came to a 5-value logic for a combinational circuit. Now what is D frontier? D frontier is if a gate input is having D, so it is capable of propagating this fault. So any one of the D value if we obtain at the output, that means we can observe the fault effect. So we will keep in this gate, if we say G1, G2, G3, G4, we will have G1 and G3 in our D frontier list. And what is J frontier? J frontier is that this input is okay. Output should be defined. Now, for having a 0 here, if it is a don't care, I can justify easily. So, input should be don't care and output is defined. Here, output is not defined, so this is not in J frontier. This is also not in J frontier. This is defined. It is B. And we have an input which is don't care. So, controlling this is possible. Applying a value here, I can generate the test pattern. So this will be in the J frontier. So now in the J frontier, we will have G1 and G4. So now what is the D frontier here for this? Any input is D. So this gate is able to propagate the D value here. So this will be in D frontier. Other gates in D frontier and no. So this has to be propagated to primary output. Now this output is defined, but inputs are if it is don't care, so it will be in the J frontier. Similarly, output is defined and input if it is don't care, it is in J frontier, and this is also defined. So this three gates remain in the J frontier. So now we will come to this. This is the algorithm of the D. Um, we actually are maintaining the D frontier and the J frontier. So I think it will take some examples and then we will see the D algorithm. So we have similarly three algorithms, D, PODEM and FAN algorithm. So before going to this algorithm, if you are having any doubts, you can ask. So let's take an example for the D algorithm. So if this node is stuck at 1, so the target fault is G stuck at 1. Now in the D frontier, so here, because this node is stuck at 1, fault free will be 0, faulty will be. So this is having a debar value. So now G is at debar. That means this gate, if we say G1, G2, G3. So if we take J frontier, G1 is having a fixed output and don't care at the input. And in the D frontier, G2 gate is having the D frontier where the D is the input. Now to propagate this fault, this has to be 1. And non-controlling value for this also. So now D bar will advance here and D bar can advance here. So we have propagated the fault effect using the D frontier through G2 and then next followed by G3. Next, now we have to do justification. So we backtrack here, it is 1 here and we want a 0 here, so this has to be 0. But you can see a conflict has occurred here. And because of this, there are no other options in the D frontier. This is the only path we had. So this G stuck at 1 is an untestable fault. Next, if we see another example, and now if we have F stuck at 0 as our target fault, this is stuck at 0. So we want a fault free 1 and a 0, so it's a D. Now in the D frontier, we will have path which is G to G4. Now we have to apply a non-controlling value here, and in the J frontier, we will have this G1 at present. Okay, G1. Now we want a non-controlling value here, so we have to justify a 1 here, so that we will obtain a D here, and we want a non-controlling value here. So we can control this, and we want a 1 here. So justifying this 1 here, we will have 0 here, which is 0 here. So it is 1 0 and B can be don't care. So this D algorithm maintains two lists like the D frontier, and it if there is a conflict, it goes back and goes to the next D frontier. And we have a J frontier where we see which back like we just go what are the inputs, like this gate is there, the output is fixed, and we see what are the inputs can be applied. These are if anyone either is uh, don't care. So the next algorithm is a PODAM. PODAM algorithm is also similar to follows the branch and bound based search, but it is not, it doesn't have any J frontier. And because of this, we will have only a D frontier, and we will be, if there is a conflict, we will backtrack to the next D frontier until the D frontier becomes empty. So the decision is selected instead of J frontier is selected using a process called backtrace, and we have some objectives. So we backtrace from the current objective. So again, we will see this algorithm using one example. So now if f is stuck at 0, if we consider, so the first objective is that we want f is equal to 1 so that we can excite the fault. Now we backtrace from the object, like this is stuck at 0. Let me take some other color. So we want a 1 here, so this is a t. Now we have to backtrace till the primary input. So we are coming to the primary input, so no J frontier, so there is no internal conflicts. So now we simulate, say considering C equal to 0. So we do the backtrace and come to C. So we search in the C is equal to 0 solution. So we perform the simulation for C equal to 0. And then we see that in the D frontier, we maintain a D frontier here also. J frontier is only not there. So we have G in the D frontier because we have a D here. So this output is in the D frontier. Now with this simulation, we will get C is 0, D is also 0. And because of this 0 input here, this is E. So E is also equal to 0. And because of it, H is also equal to 0. If H is 0, the F is actually D. With one simulation, we have obtained all these values from the backtrace. Now, if this was not satisfying, then we could have taken the C is equal to 1. Now, our second objective. In the D frontier, we have G. So, for the G, we want AND gate output this to be non-controlling value. So, we have to like consider the primary input connected to it, which is A. So, we can try simulating with A equal to 1. So, we backtrace to this objective of A equal to 1. And we simulate this A equal to 1, we see that the Z value is D. So we have detected this fault. So if we consider another circuit, So the objective is that this is stuck at 1. So B is equal to 1. Now to backtrace, we have to come till the primary input. So the primary input connected is A. So A is equal to 0. We can simulate this A equal to 0. And what we observe? B is actually D. C is, we have simulated A equal to 0, so C equal to 0. D is also 0. Because of 0 here, mask is fault. That means now the D frontier had only this gate, means this path. Had D in the D frontier, but we got D equal to 0. That means there are no other. Okay. Now the question is that can we backtrack? So we have taken a decision of A equal to 0 and simulated it. It masked the fault. So can we simulate with by taking A equal to 1? Now here itself we have masked the fault. We are not able to excite the fault itself. So again the D frontier is empty. So we say that this fault is untested. So this is the test pattern generation using the PODEM algorithm, and next is the FAN algorithm. FAN is actually the improved version of the PODEM algorithm. So it uses the concept of headlines and multiple objectives. So what is headline is that we will only justify till this point. After this point, you can see it is a fan out free network. And when there is no fan out, it's like easy to justify. We have a value, say we want a 1 here, we can obtain by controlling this primary inputs. So no need to justify till the primary input. To improve the time, we can only justify till the headlines, and this headlines is the position point where before that the circuit is not having any fan outs. It's a fan out free network, and this portion can have fan out. Okay, so we will be justifying till x and y, which is the headlines, which before which the combinational circuit does not have any fan out. And the next improvement is that we will use the multiple objectives. Now, what is the multiple objectives? So at the times before we were taking k equal to 0 as an objective, but now we will take the objective of both k equal to 0, m is equal to 1, so that if there is any conflict, we can identify. So we can backtrace from k equal to 0, and k equal to 0 may be like 0 here, 0 here, a 0 here. Having a 0 here may violate this. So when we have now we can change this because we have this objective in the our objective list, such that we can have 1 here, and now obtaining a 1 is easy. For having a 0 here, we need more 0. So in this way we can have multiple objectives. So this way we are making the backtrace more intelligent to avoid the future conflicts. Next we have the concept of static implications, static logic implementations. These are the further methods to help ATPG make better decisions. And this can reduce the conflicts, also the number of backtracks. So what is the idea of, like, what is the effect of asserting a logic value to a gate on another logic value in the circuit. So if we consider this, the first method, direct implication. Now, if f is equal to 1, this directly implies all these values. You can see D should be 1, E should be 1, G becomes 1 because this is a buffer, and because it's an OR gate, J becomes 1, and this is also OR gate, K becomes 1. So with one implication, we have all these values. Similarly, if we have J equal to 0, where is J? J equal to 0, the implications directly imply G and H should be 0. And which means F is 0, which means W is 0. Between these two, we don't know which is 0, so we can leave. And this is 0, so X becomes 0. Because any one of the gate is 0, we get this also 0. So in this way, we with one value, we can have the implication, direct implications. We have some called as indirect implications. That means these are already defined. F is 1. Because of 1 here, we need both to be 1. Because of a 1 here, we have 1 here which gives J to be 1 and K to be 1. And what is indirect implication? Because of this and this being 1, X is 1. The next level of simulation. So this is repeated for every node in the circuit. Next is the extended backward implication. So from the direct implication, we said that if F is 1, D and E became 1, G became 1, J is 1, K is 1, and X is 1 because of the indirect implications. Now backtrack implication obtained by enumerating cases for unjustified gates. So now the unjustified gate is this D equal to 1. Can we backtrack this? So this can be having options that we have a set SA and SB where A equal to 1 and B equal to 1. The intersection of these two set can give F is equal to 1 which implies C is equal to 0. So this is repeated for all the unjustified gates, and this is all performed to improve the ATPG time. The static was that we didn't have any other values fixed. This was like completely all values are don't care. In the dynamic, we have a particular value to be fixed. Say suppose C is 1. We can't change the C. C is already assigned. In such a way, in such a case, and we want to obtain a 0 here, how can we perform the implications? Uh, Actually, we want Z to be 0. So we want either this to be 0 or this to be 0. But C is 1. So this is called as dynamic logic implication. Now another example, if we have a D here, suppose. So we have to propagate this to Z, and if we have F is equal to 1 is the necessary condition. This is a non-controlling value. It can be either propagated through this path or this path. So to take this further, the intersection of all the necessary assignments for all fault effects in the D frontier can be taken. So D frontier has two gates. Now what is evaluation frontier? So if this is the evaluation frontier, we know all these values. Now for any other circuit, for any other fault, we have the evaluation frontier as 1D010. This primary input will deduct that fault. So if say F1, this is the D frontier, E frontier of F2 fault. For F1 fault also E frontier is same. Then the primary inputs will detect F1 also. Then next is the fast untestable fault identification. So these are untestable faults which cannot be excited, or we are not able to propagate, or we are not able to both excite as well as propagate. These are some combinations of fault which we say that it's an untestable fault. So, and also why when ATPG is taking lot of time, we drop such faults, and those faults are also untestable fault. So if we can avoid what are the untestable faults, we can remove them from the fault list so that ATPG can become little faster. The next concept from the paper, and the name is fire. It's based on the conflict analysis. So if S0 is a set of faults that are untestable, when the signal is S is equal to 0, this fault must require S is equal to 1 to be detected. And if S is equal to 1, set of faults that are untestable when S is equal to 1. So this exciting will need an opposite value S is equal to 0. So intersection of both S0 and S1 will be untestable because they require both simultaneously S0 and S1. So with this we will see through an example. Now we want to imply B is equal to 1. B is equal to 1 implies B1 and B2 1. And OR gate input is 1, so D is equal to 1. This is X naught, so it's a 0, which means D is 0. So faults which are unexcitable when this B is 1 will be the B stuck at 1, B1 stuck at 1, B2 stuck at 1, and D stuck at 1, because we need an opposite value in those nodes, and X0, Z0. What are the faults which are unobserved? A fault will be unobserved because of a controlling value there. And similarly E1, E2, and similarly Y fault. The intersection of this, the faults untestable when B is equal to 1 are intersection of both A0, A1, B0, B11, B21, D1, and then followed by E1, E0, and E2 getting stuck at 0, E2 getting stuck at 1. So this we can get all the undetectable faults by performing this conflict analysis. Similarly, for another implication, when B is stuck at 0, this implies this are 0. Now, because of controlling value to the AND gate, Y becomes 1. This is anyway non-controlling. E1 becomes 0. So the faults which are unexcitable will be the faults in these nodes B0, because which needs opposite value. Unobserved wherever we have a controlling value. So B2 was having a controlling value. So this fault will be unobservable because of a controlling value. So the faults which are undetectable will be the intersection of union of both. So both this and this union. Sorry, this intersection with union. Similarly, next example. Now that two sets of the faults undetectable, when B0, B1 we have obtained. Now the intersection of these two sets are those that require both B is equal to 0 and B is equal to 1 for detection. So those faults are undetectable, untestable faults. So the pattern, we got some faults which are undetectable when B0, B1. The intersection of both means that that fault requires both 0 and 1. So such faults are the faults which are untestable faults. So in this way, performing the conflict analysis, we can detect all the untestable faults. The simulation based ATPG is the random or the the weighted random based ATPG methods. ATP random and weighted random based test pattern generation methods. The challenge is that how can we guide? Like if we are saying the weight, how much weight can we give or the bias? So these are the challenges, and what we call that random or weighted random is the simulation based ATPG. So next we will solve some questions. In a combinational circuit with multiple outputs, a maximum of 5 primary inputs of can lead to the one output. What is the deduction probability of the most difficult deductible fault? These are the questions taken from the previous year assignment. So we have already seen the d-min, which is the deduction probability of the most difficult fault, which is greater than or equal to 0.5 to the power n max. And it's given that n max is equal to 5. So the d-min is greater than or equal to 0.5 to the power 5, which is 0.03125. So the correct answer is option C. So the next question, use the Boolean difference method to find out the input pattern that can deduct the stuck at 0 fault at input Z. So this node is stuck at 0. And we have to use the Boolean difference based method. So first let's see what is the value of P. P is X, Y, Z bar plus Z. Can you simplify this expression? Let's use a K-map to see whether we can simplify this. So it's Z is equal to 1, means this region, and XY Z0. So with this we have XY plus Z as the simplified expression. Now what we have to put is, to excite this we need a 1 here. So we need to multiply with Z. The first is XY plus Z equal to 0, XORed with XY plus Z equal to 1. So this gives Z XY XORed with 1. So XOR gate output will be inverted and any one of the input is 1. So we will get X bar Y bar, XY the whole complement. Now we will apply the De Morgan's theorem, X bar plus Y bar. So we pattern will be X complement Z plus Z Y complement. So this pattern, if we write it, it will be X, okay, I write X Y Z plus X bar Y bar Z plus X Y bar Z plus X bar Y bar Z. These are patterns. Will 0 1 1, or it can be 0 0 1, or it can be 1 0 1, or it can be 1 1 0 0 1. So these are the three patterns possible, which is this is also pattern, this is also pattern, this is also pattern. So all of the above is the correct answer. Any doubts? Okay, so we will go to the next question. From the following circuit, identify the gates that represent D frontier and the J frontier. Here we have a D. So Q can be able to propagate the value, and R can also propagate the value. So because these are non-controlling, and that's why it is a don't care. So the D frontier will have Q and R. So this will be in. And next, J frontier output is defined, but inputs are don't care. So P is the J frontier. Output is defined, inputs are don't care. So again, this is also a J frontier. So P and S are J frontiers. Option B. So with this, we'll go to the next question. Find the test pattern to detect the stuck at one fault at X and Y in the following circuit. So let's consider this is stuck at 1. If this is stuck at 1, the fault C should be 0 and fault D should be 1. To obtain a 0 in our gate, we need both to be 0. And a 0 will be applied to this AND gate. This will be D bar, which will be masked. Is there any other option we have? No other way to propagate this. So we cannot excite and propagate at the same time. So this fault remains untestable. So X stuck at 1 is untestable. The next fault is Y is stuck at 1, which means again 0 bar 1, which is D bar. To have a D bar here, we want a non-controlling value here. And this is an OR gate, we want a 0 0 here, 0 0. This has 1. With 1, again we have a conflict here. So again, Y is also stuck at 1 is untestable. So both X and Y are untestable. The next question. Read the following statement and find out the pattern generation technique for the fan-out free circuit described by these statements in the given order. So if we are able to perform multiple objectives, we have seen that it was an improvement from the Podum algorithm which was possible in fan. And we had D frontier and J frontier in the D algorithm only. Because in the Podum algorithm, J frontier was removed. Backtrack but not use J frontier. That was in the Podum. So this is fan D algorithm and Podum, C option. So clear any doubts? So the next question, a circuit has K, E of K represent the set of unexcitable faults. So which we saw the first set with, and then OK, which is unobservable faults. Select the expression that describes the undetectable faults. To have an undetectable faults, we said that E of when k is 0, uh, and this we perform the union operation, and both, because both unexcitable and unobservable faults, both will be masked. So we perform the union operation, and then we said that the intersection of both of this, that is, will require a pattern which requires both k is equal to 1 and k equal to 0, which is not possible. So that fault will remain an undetectable fault. Any questions? Let's solve one question using the D algorithm. This is the given circuit. So we have a stuck at 0 fault here. Consider this. To excite this, we need a 1. So which means 1 by 0, which is D. Now let's see what is in the D frontier. If we consider this to be G2, G3, only path is through G3. And what we have to justify? J frontier. But to excite the fault, G1 has to be justified. What is G1? It has to be 1. So this and this needs to be 1. Next, to propagate this fault again in the J frontier is J. If this is 0, output is defined, input is having don't care, so J2. This J A equal to 1, B equal to 1. Now this we want to define what is C. C can be anything, don't care. So the required pattern is 1, 1, don't care. Because for an AND gate, if one of the input is 1, the output is going to be anyway 0. And for a NOR gate, non-controlling input is 0. Okay, next we will see one question on redundant circuit. So these are the faults which are also known as untestable. This can be deducted using untestable faults. Untestable faults are indicate redundant circuit. Now how this can be used to reduce a circuit? Let's see. V A D. Let's consider D is sector 0. Now if this is stuck at 0, we want a 1 here, which means 1 by 0, which is D, and a 0 here. A 0 here will make this output 0 anyway. So here we got a conflict. So we say that D stuck at 1, is untestable fault. So now how can we reduce this circuit? This input to an OR gate can be connected to a ground because it's stuck at 0, it says 0. And this B A. This is E. OR gate one input is 0, which is non-controlling value, which is like B. So it's like B. This is going to be coming here. So it's like B connected to E. It's just a straight line. So this is how we can simplify it. Now let's just write a truth table and verify this. What will be D? D will be 0, 0, 0, 1. And what will be E? E is an OR operation between D and B. 0, 1, 0, 1. So you can say both D and E are same. We can also write the expression for E. E is equivalent to AB plus B, which is equivalent to, okay, I'll write there. Now let's simplify using the Boolean based method. A, B plus B, which means, which is equivalent to B common A plus 1, which is equal to B. So E is equal to B. This is the redundant fault, like untestable fault, which is indicating a redundant circuit. So next we will solve some more questions on the Boolean difference based method. So let's consider a circuit Fg x3, x2, x1. So what is the f of x value? Which is this f? I take f itself. It's x1, x2, all with x3. So what is the difference equation? df by dx2. If we want, say this is stuck at 0. Difference equation has to be written with respect to x2. So we want x1 and x2 is 0. So 3 is 0 plus x3 XORed with x1 dot 1 plus x3. And we want 1 here. So it should be x2, x3 XORed with x1 xm plus x3 equal to 1. x3 complement x1 plus x3 plus x3 x1 plus x3 whole complement and whole term multiplied with x2. So x2 x1 x3 complement plus x3 x1 bar x3 bar. This will be 0. So x1 x3 bar x2. Okay, right. x2 x3 bar. That means it's 1 1 0 is the required placement. To verify this, we want a 1 here, so x2 is 1. And we want to propagate this 1 by 0. 1 by 0, so non-controlling value, this should be 0. To have a 1 here, have a non-controlling value here, 1. This is also non-controlling. So the test pattern are 110. So next, one more question we will see on the Boolean difference based method. This is also based on the Boolean difference. If we consider this to be 0 to be 0, x to x, this node is h, and let's consider h stuck at 0. So what is f? It is x1. We want in terms of h, we have to write the function in terms of h. And what is the actually of h? It is x1. Now let's come for h stuck at 0. So we want h to be 1, and this expression h should be 1 first. So x1 plus x2 XORed with h is 0, so x. Now it is x1 plus x2 whole complement x1 plus x2 x1 complement. This will be x1 complement x2 complement x1. This will be 0 plus x1 bar will go, so x1 complement x2 multiplied with h. So it is, what is the value of h? H is x1 complement x2. So we want a 0 here and a 1 here. So this is also not equivalent to 1. So this fault is also untestable. Now if we consider h is stuck at 1, that means for h it should be 0 to excite the fault. So we will write h complement. And the expression x1 complement x2. What is this? H complement is x1 complement x1 x2, which is um, some error in the question. Here it should be x1. Yeah. Yeah. So it is x1 complement x2, which is equal to 0, not equal to 1. So this fault also remains untestable fault. So this was Boolean difference method showing for some untestable faults. Now again we will take another Boolean Difference. Next question. G H Z A F D C and E. We want E to be stuck at 0. So exciting, it should be 1. Let's write what is the value of, and we are writing the Boolean difference, generating the test pattern for E stuck at 0. So Z is A C complement plus E T. We have an expression with E. And actually E is nothing but C. So what is, we want stuck at 0, so E, and the expression when E is equal to 0 is A C complement XORed with, when E is 1 it is A C bar plus B. So it's E AC complement, the whole complement, AC bar plus B plus AC bar plus B, the whole complement. So this gives AC bar plus C, AC bar plus B plus AC bar whole complement plus with E. So here we have E, A bar B plus B plus AC bar, A bar plus C plus further simplifying A bar B plus BC plus AC bar BC. So it's A bar B plus EBC plus A C bar B bar. E is nothing but C, so this is 0. Again it's A bar BC plus BC. So the test pattern can be 0, 1, 1, or A can be 0, 1, 1, or A can be 1. Let's do this through our method. Now to justify this, we want a 1 here, a non-controlling value here. So here the value will be 1 by 0, which is D. So output we want a D. So this output we want either D or D bar. So this should be a non-controlling value. We have a 1 here, so it is automatically 0 here. So this can be don't care. So we have obtained as a requirement. Any doubts? Okay, next we will see another question. Construct XNOR operation for 5-value logic. We have already seen the 5-valued logic for AND, OR, and NOT. Now let's see for XNOR gate. So the normal XNOR truth table is 0, 0, 0, 1, 1, 0, 1, 1. It's 1, 0, 0, 1. This is the normal truth table, like our truth table, 2-valued logic. Now let's write for XNOR. 0, 1, D. We know D is 1 by 0. D bar, which is 0 by 1. And X, which can be either 1 or 0. 0, 1, D, which is 1 by 0. B bar, which is 0 bar 1. And X. So any values don't care for X0, it will remain don't care because there is no controlling value. Based on another input, it will be either a buffer or a semi. So this 0 will be 1, 1 0 will be 0, 0 1 will be 0 1. Now D, which is 1 0 0, so D bar 0 0 1 1 0 0, so D 1 1 1 0 D. Opposite is a different value 0, same value 1, so D. Again, so it's D bar D. This will be D bar because it will be 0 by 1, and this will be 1 by 0, which is D, and this will be 1 by 1. This will be 0 by 0, so 0. Again, this will be 1 by 0, so D. 0 by 1, so D complement 0 and 1. So this is the 5-valued logic table for the XNOR gate. So any doubts? Any questions? So today we have seen the test pattern generation. So we have used the ATPG and the fault models we described, and we started with the Boolean difference based method to generate the test patterns. And then we came to 5-valued logic and a basic ATPG without which will use for fan-out free circuit. And then we came to D algorithm, which can be used for any arbitrary circuit, including the fan-out if it has. So it uses both D frontier and J frontier. And then next we came to another algorithm, which is modem. In this algorithm, we said that the J frontier is not needed, so we will perform backtrace and we will have an objectives to directly to the primary input. And so we solved some examples. Then we saw fan based algorithm, which is similar to modem, but we have charged it. The fan algorithm is similar to modem algorithm, but we use the concept of headlines, where the headline is this is a node, a headline, node X. Before that, all the circuits are combinational circuits, which are fan out free circuits. So we will be justifying till these headlines, and at the objectives we will consider multiple objectives so that we can avoid the conflicts. And further, we have seen some other methods which can be used for ATPG to make better decisions, which are direct implications. So one, we have one value, what are the values we can directly imply, and one step simulation, what are the values can be implied, like obtained by simulating the direct implication. And then we saw what are the values which is needed through backward implication. And dynamic implication, logic implication was when one of the node value was actually defined it. In the static, all the nodes were in don't care, but in dynamic, one node is, suppose a node is already assigned to a value. And then the another method we saw was that if the E frontier is same, for another fault also, then the test pattern, the primary input will remain the same. And next way, what are the ways we can detect the untestable faults? And what is untestable faults? Either we are not able to excite it or propagate it, or simultaneously excite and propagate it. So we saw a method called fire, which we said that if a node, we set it and we obtain some unexcitable and unobservable fault. So undetectable faults will be the union of these two, and similarly with b equal to 0, and the intersection of both will be the untestable faults. And simulation based ATPG is the random or the weighted random based ATPG. Weighted based the test pattern generation, and we have seen some questions based on the D algorithm Boolean difference. So any doubts? Verification book, I am not sure, but for this testing, I think you can follow this book. This book follows the similar approach. This is the book. So I have also taken some of the questions from this book only. So you can see the similar concepts, all the concepts. So for testing, you can follow this book. For verification, I am not sure. Static timing analysis, also I am not sure about the books.